Okay, good morning, everybody. Today we're going to talk about a classic mechanical engineering topic, and that is the topic of garden hoses. Right now, typically garden hoses are green. I've actually got some gray ones, some green ones, and some white ones, but we'll just go with green for now. And let's say it's that long. Now, if we connect this hose to our house, here's our house. The water pressure in your house is, for the sake of easy numbers, 100 psig. What does that mean? That means it's 100. It's pounds force for every inch squared. Right? That's a pressure, force per area. And the gauge pressure, this G means it's actually a gauge pressure. What is gauge pressure? That is, how high is the pressure above the local atmosphere, right? Typically, the atmosphere is about 14 pounds. So this would actually be 114 pounds, but it's easy to reference everything to the atmosphere. You'll learn much, much more about this in ME 363, and that's fluid mechanics, which is an awesome class. I hope you enjoy it. And then out here on this end of the hose is your yard. And we'll say the yard is at 0 psig. Now, if I just take the hose and I hold it upright, the water kind of bubbles out of it. It doesn't really spray. Of course, you can do the trick with your thumb or put some sort of a nozzle on the end. We'll talk more about that in the Thermo 361, Fluids 363, etc. But anyway, let's just say that your house is at 100 psi and your yard is at 0 psi. Well, this is a really high pressure over here, so we'll draw that with a big P, really high pressure here, and then over here, down on this end of the thing, we've got a little p for little pressure. So we've got big pressure on one end, little pressure on the other end, and so what happens? Well, the water flows this way. Right? Why? Because it flows from high pressure to low pressure. I think we probably all know that. It starts at 100 pounds, but then I should make a note that there's these little, let's make this really small here, little bumps in the hose that resist the flow. So as the water flows along the hose, the little bumps kind of gobble up some of the pressure. So by the time it gets to the end of the hose in your yard, there's no pressure left, right? Or it's down to 0 psi. It's not a total vacuum, but you get it. Again, you'll learn much more about this in fluid mechanics. But this talk really is not about garden hoses. Really, we're trying to talk about electricity. So let's draw a wire here. Here's a wire. We'll slide that back down to there about. So this is actually an electric wire. And let's say we connect one end of the electric wire to, let's say, a 12-volt battery. I'm going to make my writing just a little bit bigger. With 2.0, that's too much. 1.5, there you go. So let's hook this up to a 12-volt battery. All right, so that's V for volts. And then the other end will connect to 0 volts, or that's another term for that is ground. Now, maybe some of you have learned about this in high school. I'm not sure. So we'll review just in case. Now, we know that something's going to happen. Oh, there's something important about the garden hose I forgot. I actually recorded this once before. You want to see this? I just did this whole thing, but I forgot to record it, so I'm doing it over. In your backyard, you have a very curious, very inquisitive, and somewhat reckless daughter, and her name is Cece. She's 6. Cece sometimes plays with tools she shouldn't, but I hate to discourage scientific investigation. So Cece takes her razor knife that her dad left loose in the shed, and she cuts a little hole in the hose here, right? Well, what's going to happen? Some of this water is down here. It's just going to come squirting out. Right? And it doesn't squirt out a lot because there's not a lot of pressure down on this end of the hose, so it squirts out about that high. And so we'll measure the height of that as kind of a, we'll say that this little dimension here, you guys know what dimensions are, we'll call that a low pressure leak. Right? So sorry, but we're not quite ready for the wire yet. We're still doing the hose. And then on this end, she says, well, that's not very exciting. She was hoping to really make something fun so she and her friend Wendy can play in the water. So Cece says, well, I can do better than that. So she goes over closer to the house and then makes a little cut there. What's going to be different? How is it going to be different when she cuts a hole in the high pressure end of the hose versus the low pressure end of the hose? Well, she's going to get a much more interesting, much more fun leak that sprays way high up in the air like this, right? It's a really tall leak here. And so that is what we call a high pressure leak. We got a high pressure leak there. It's a high pressure leak because it's close to the high pressure end of the hose. Here we have a low pressure leak because it's near the low pressure end of the hose. The same thing goes for the electric wire, right? I know I've got high pressure on one end. Let's make that really big. So we've got big high voltage down here, high voltage, and then on the other end we've got just some little bitty, not even two. Let's go down there. We've got a little. What happened there? Redo that. We've got a little low voltage there. Well, what's going to happen with that? Same exact thing. The electric current. Electric current flows this way. Right? What do the electrons do? They get pushed from the high voltage end of the wire to the low voltage end of the wire. And similar to the garden hose, we can say that there's the metal in the wire, right? It does two things. It simultaneously allows the conduction, but that gets really, really complicated. The metal in the wire resists the flow. Wow. Wow, that's almost just like the garden hose. Well, it wouldn't really be a mechanical engineering lecture, right? And it's a stretch to call this a mechanical engineering lecture, unless we had some equations, right? So let's assign some value to the resistance. The resistance for this particular wire, for lack of a better, keep the easy numbers, so we'll call this 10. There's a funny symbol, right? That is the Greek letter omega, capital omega. Right there. That's a Greek, and that means the resistance is 10 ohms. 10 ohms, right? Because ohm is the guy. I don't know where ohm is from. Germany, maybe England. I don't know. But Ohm came up with this relationship between voltage, resistance, and current. All right, so let's take a look at that. Ohm's law. Ohm's law says this. That's not current. Increases with increasing voltage difference, right? So the bigger the voltage difference is, the more current flows, and decreases with increasing resistance. Right? So the bigger the voltage difference, the more current's going to flow. The more resistance, the less current flows. In fact, this is one of the easiest relationships we have. We can say that I, and this is the current, in amps equals the voltage difference in volts divided by the resistance. Resistance in ohms. I think that's supposed to be capitalized because it's after a name. But these old scientists get enough credit, so lowercase o. So in this particular case, this particular wire, let's see if we can figure out what the current is. The current will equal, well, there's a 12 volt difference divided by 10 ohms. So we will get 1.2 ohms. Nope, not 1.2 ohms. Stop that. We will get 1.2 amps. So that's amperes. But we usually just call that amps. So through this wire, we'll have 1.2 amps. All right. So that's Ohm's law. All right. Let's put a red box around that because that's going to be pretty important for the rest of our semester, or at least the next couple of weeks. We think. We don't know. We don't know what's going on. All right. So Ohm's law. All right. Now this is a nice picture of a garden hose and a wire, but let's draw this as an electrical engineer, or for that matter, a mechanical engineer would do it. So I think we can add a new page by doing this. There, that works. So now we have a new page. So draw with symbols. We'll draw the same exact thing, right? Where I'm just going to draw a node here. This is a node. And I'm going to say this node is at 12 volts. And then let's say I've got, and I'm going to go here, and I've got, this is a resistor. And then we've got another node at 0 volts. And so this thing here, sometimes we draw little dots at the end of the resistor, is a resistor. Right. And this one could be 10 ohms. And so this is exactly the same as the picture we just drew before, except it's with symbols. And we know that I is the voltage divided by the resistance equals 1.2 amps. All right? Well, what if we mix this up a little bit? Now, I shouldn't have picked 10, and you'll see why in a second, but I'll just have to do some quick mental arithmetic. I'm 47 years old, but I can still do a little quick electrical calculation. Let's do the same thing, except let's split it into 2 resistors. So here I still have my 12 volts, and here I still, let's say I have a, I don't know what's going to make this easy for me, but I'm just going to punt here, and I'm going to say this is a 3 ohm resistor, and that's connected to a 7 ohm resistor, and then that's connected to ground, 0 volts. We call that ground. Now, 3 ohms plus 7 ohms is still 10 ohms, right? So this is all, these pictures are more or less the same. The difference is now we have 2 resistors that equal to 10 ohms. I know that big picture for this particular setup, it's still 1.2 amps. Oh, this is going to go bad for me. 1.2 amps flows. Right, so I know I've got, let's draw blue for the flow. I know I've got 1.2 amps is going to flow all the way through here. All right, but what if Cece came along and instead of, putting a, cutting the garden hose, she takes her multimeter, and yes, Cece actually has a multimeter. We were at Menards one time, and she really wanted a new tool. And so we were in the electrical section, and I was like, hey, how about a multimeter, Cece? And she's like, yeah, cool, multimeter. So my 6-year-old daughter has a multimeter. And so she cuts right here. Well, there's going to be some leak, right? And the height of this leak is indicative of how much pressure is at this point. Or actually, the height of this leak is actually indicative of some voltage there, right? I know it was 12 volts on the left end. It's 12 volts here, and it's 0 volts there. But what is the voltage right in the middle there? Well, we can figure that out with Ohm's law. Right, I know that the current equals the voltage difference divided by the resistance. Well, I can also say that the voltage difference equals the current times the resistance, right? So in this case, if I draw it up here, or if I draw it for, let's see, what color am I going to do here? I don't know what I'm going to do. I'll just leave it in black. So the voltage difference for this resistor means that V equals, well, I know there's 1.2 amps flowing through there. And I know that the resistance is 3 ohms. So that means that my voltage at that location, or the voltage difference is 3.6. So this is the voltage difference. Across the first resistor. Okay? All right. Which means the voltage here, I can answer this question, is, it started at 12, it dropped down by 3.6 across that first length of hose, or that first length of wire, or that first resistor. And 12 minus 3.6, I think, is 8.4. Right? Okay, so it's 8.4 volts there. And then so we can continue this calculation. Let's see what happens here. The voltage difference here equals 1.2 amps still, times 7 ohms equals, oh, interesting, 8.4 volts. So it drops another 8.4 volts across the second resistor. Now let's draw this one to here, which means the voltage here must drop all the way down to 0 volts, which we knew to start with. All right. So hopefully you've seen this before. If you haven't seen this before, please come to office hours and get a little more description. But there's one more thing we have to do. So let's add one more page here. Now we're going to talk about a potentiometer. Now this is, I'm hesitant to say this because sometimes you're not supposed to be really honest when you talk about types of people. Electrical engineers tend to make things way more complicated than they need to be. Specifically, electrical engineers also like to use bigger words than they need to so that they sound smarter. What a potentiometer actually is just, redo that. Redo. There we go. What a potentiometer is really just a variable. A variable resistor. Now, I do appreciate electrical engineers, though, because they use symbols that make sense, so they're not all bad people. So let's say we have 100 ohm right. So what it really is, is just a big long coil of wire. And there's a big long coil of wire like this. So coil of wire. And then what they do is they take a needle, and it's literally a needle. And the needle, what color is a good color for a needle? Maybe gray. All right, sounds good. And so the needle just kind of rides on here like this. I gotta make that a little bigger. So that's a needle. And then the needle is connected to another wire, like this, right? So if I sent the electricity, if the electricity had to go all the way through here, right, that would mean it goes through 100 ohms of resistance. But if I give it a shortcut, right, so the needle acts as a shortcut here. As a shortcut. Hopefully everybody knows what a shortcut is. It just means a shorter path. Right now the current, and I got to make this a little fatter here so you guys can see. So if I went through this way, so that only means that's a little less than half. So that's like 40 ohms. Let's do that. I'm going to run into trouble quickly here. So this is going to be like 40 ohms. So, because it doesn't have to go through the whole coil of wire. And then alternatively, so if the electricity went through, I'm going to pick a different color. This is not a garden hose, but I'm doing my best to keep this clear. The electricity could go through this way. And that would be only like, let's see, if the one side is 40. So 40 ohms worth of wire on that side, so that means there must be 60 ohms. 60 ohms worth of wire on that side. All right. The way we draw that in symbols, and this is where I do actually like electrical engineers, because they have good symbols. The symbol for that looks like this. I've got a dot. I've got the standard resistance symbol, another dot, and then an arrow. I don't know if that arrow is sometimes a little fatter arrow or what that is. And that's got another dot on the end of it too. All right. So if the total is 100 ohms, then, this distance, so let's call that R1, and then this distance here, R2, is R1 plus R2 equals 100 ohms, right? So I could physically move this needle. Now, I apologize for the sloppiness. I could move the needle, and the way this works, there's a little, something like usually a little screw that you turn. Right, if I move the needle all the way to one side, so if I move the needle all the way over here, right, then this one would be, I'd basically have turned this into a 0 ohm resistor and a 100 ohm resistor over here, right? So between the first two pins and the second, between the first two pins on this potentiometer is 0 ohms, and on the second two pins it's 100. Right. Likewise, I could put the needle all the way to the other side, and then it would be, 100 and 0. Just for the sake of time, I'm going to draw a little picture. I've got a potentiometer around here somewhere. So let's go to one more page, and so physically, what the potentiometer actually looks like, it's usually, for whatever reason, they make these electronic components blue. So it's this blue box. And then on the blue box, I'm going to make that a little bigger actually. So it's a blue box that looks like this. And then on the blue box is a metal, like a metal screw. Let's do that, maybe dark gray. And the metal screw sometimes has like a little screwdriver thing on it. So it looks like a little screwdriver. So you can adjust this with, turn this to adjust resistance. And then at the base of this thing are 3 little leads. that fit nicely into your breadboard. And then so, you imagine that this thing is just, it's a coil of wire with a needle that scrapes over it, and it kind of creates a shortcut. So this is the needle. And this is terminal 1. And this is terminal 2. Right? And then we'll divide this into resistances. Yeah, I'm running out of what color should I do that. I'll do that in green for no good reason. So this resistance is R1. This resistance is R2. And this resistance is R of the whole potentiometer. Right? Now, your Arduino kit, probably came with a potentiometer. They almost all do. If it didn't, talk to us and we'll try to find you a potentiometer. And it might be a 100 ohm potentiometer, it might be a 200 ohm potentiometer, it might be a 1 kilo ohm potentiometer. So let's actually make a quick list. Common potentiometers. Oftentimes they come in 10 ohms, or sometimes they're 100 ohms. For whatever reason, 220 is a common size. 1 kilo ohm, right? So that means 1,000 ohms. 10 kilo ohm. Right? I don't know what size potentiometer came with your kit. Maybe your kit tells you, maybe it doesn't. But you know what we could do? I bet we could do an experiment to figure it out. Okay, so we'll talk about that next.